Good day, ladies and gentlemen. My name is Karol Bartosiewicz and I am from Institute of Physics, Kazimierz Wielki University in Poland. The topic of my presentation deals with the enhancement of exciton luminescence in LuAG single crystals by lantern doping. My presentation consists of three parts. First, I will talk about the background related to the problems of exciton luminescence in the LuAG single crystal and motivation for this research. Next, I will move on to show and discuss experimental data, and in the end, I will summarize my research. Let's start with introduction part. LuAG single crystal activated with cerium is a very well known and very well studied material showing promising properties to be used for gamma and high energy particle detection due to high density, good radiation stability, fast scintillation response, light yield of about 25,000 photons per 1 mega electron volt, and well-mastered crystal growth process enabling to grow a single crystal with a few inches in diameter. However, high temperature crystal growth process creates many shallow trapping centers which significantly diminish light yield and timing performance. Such shallow trap centers arise due to the displacement of some part of lutetium atoms to aluminum sites and forms so-called lutetium-aluminum andesite defects. Lutetium at aluminum site increase covalency in the octahedrons. At critical values of non-Coulomb potential, the energy levels of cation or oxygen split off into forbidden gap, forming electron and hole trapping centers. As we can see in this figure, the andesite defect emission in undoped LuAG shows strong luminescence with intensity close to the intensity of cerium luminescence in this matrix. This means that andesite defects are very efficient in electron trapping. In LuAG, the concentration of lutetium-aluminum andesite defects could be up to 5 atomic percent. Such high content of andesite defect can efficiently compete with activator like cerium or praseodymium in capturing electron from the conduction band. Consequently, a significant amount of the excitation energy is wasted, which means is not delivered to activator. Therefore, the motivation for this research is to enhance the exciton emission that is bright in LuAG crystal. Lantern doping into LuAG lattice can cause the displacement of small-size lutetium cations from the dodecahedral positions into octahedral positions, thereby increasing the concentration of lutetium-aluminum defect. In lantern-doped LuAG, we can observe three types of exciton luminescence. At low temperature, exclusively self-trap exciton luminescence at 250 nanometers. At room temperature, arise luminescence of exciton localized and bounded at lanthanum lutetium center at 280 nanometers and luminescence of exciton localized and bounded at lutetium-aluminum andesite defect. Let's move to result and discussion part. This slide shows a simplified scheme of the micro-pulling down method which I use to grow the single crystals. The conditions are as follow. As an atmosphere, I use nitrogen with the gas flow from the top. These pictures shows the as-grown single crystal rods. As we can see here, with increasing lantern content, the surface becomes more opaque and the end is conical, as well as the edges of cross-sectional plates become more cloudy. This observation might suggest that lantern atoms hardly substitute lutetium atoms in LuAG crystal due to large ionic radii between lanthanum and lutetium, which is around 16.3 picometers. This slide shows the XRD diffraction pattern for all crystals. The only pure garnet phase was detected. Radioluminescence spectra recorded at room temperature are shown in this figure. The dominant luminescence in the ultraviolet spectral range in the undoped sample has lutetium-aluminium andesite defect origin, whilst in lanthanum-doped samples, the ultraviolet emission is caused by both lutetium-aluminium andesite defects and lanthanum-lutetium defect centers. Both kinds of centers can localize and bound charge carriers, followed by the formation of excitons. Their radiative recombination causes intense luminescence in the ultraviolet spectral range. In undoped and slightly lanthan-doped crystals, also terbium-3+ trace impurity luminescence is observed. Interestingly, the dominant luminescence moves its position gradually from 292 to 275 nanometers with increasing lanthan content. It should be noticed that luminescence at 292 nanometers in the undoped LuAG belongs to lutetium-aluminium emission center, whilst the luminescence at 275 nanometers in lanthan-doped LuAG is ascribed to lanthanum-lutetium emission center. Moreover, lanthan doping significantly increased the intensity of ultraviolet luminescence. These figures shows liquid helium and room temperature photoluminescence spectra for undoped and lanthan-doped LuAG single crystals excited at 170 nanometers. Spectra recorded at both temperatures show significantly distinct profiles. Namely, emission spectra recorded at liquid helium show three broad bands centered at 250, 415 and 475 nanometers. Interestingly, the position of the emission centered at 250 nanometers is independent on the crystal composition changed, and it is completely quenched at room temperature. Hence, this luminescence might be connected to the radiation relaxation of the self-trap excitons. Emissions at 415 and 475 nanometers belongs to F+ and F centers. Spectrum for undoped LuAG crystal recorded at room temperature shows noticeable emission of terbium-3+ trace impurity ions in the visible spectral range, which significantly decreases with increasing lanthan content. Interestingly, the ultraviolet part of the spectra consists of a broad emission band centered at 292 nanometers for undoped and 275 nanometers for lanthan-doped LuAG crystals. The luminescence at ultraviolet spectral range has exciton nature. This slide shows liquid helium and room temperature excitation spectra for emission at 250 and 275 nanometers respectively. At liquid helium temperature, the excitation spectra of self-trap exciton luminescence in undoped and lanthan-doped LuAG single crystals show strong absorption at the fundamental absorption edge, confirming its self-trap exciton nature. Interestingly, with increasing lanthan content and thus the content of impurity centers, the excitation bands become broader. This fact might indicate that radiative annihilation of low-energy excitation takes place mainly at the irregular, perturbed sides of the crystal lattice, which means stabilized by lanthanum-lutetium centers. The same trend is observed in the excitation spectra recorded at room temperature. and at 275 nanometers, where the bounds are and the excitation spectra, both recorded at liquid helium and room temperature, are located on the boundary of the fundamental absorption edge. This slide shows room temperature decay curves for undoped and lanthan-doped LuAG crystal for emission at 267 and 300 nanometers, excited with pulse soft X-ray. Decay curves were recorded at the high energy and low energy sides of the emission band to well separate decay time components coming from lanthanum-lutetium and lutetium-aluminium emission centers. The decay curves for undoped LuAG crystal recorded for emissions at 267 and 300 nanometers are similar with comparable fitting parameters. This observation confirms that the emission band, centered between 200 and 400 nanometers, is caused by at least two types of luminescent centers related to lutetium-aluminium andesite defects, namely the luminescence of exciton localized and bound at lutetium-aluminium andesite defect. The decay times for lanthan-doped samples recorded for emissions at 267 nanometers are approximated with triple exponential function, while for emission at 300 nanometers by the double exponential equation. Such a multi-exponential character of the decay curves is another proof that there are at least two distinct luminescence centers. Those centers are lanthanum-lutetium and lutetium-aluminium, which can bound and localize exciton, causing strong luminescence at ultraviolet spectral range. The conclusions are as follows. I would like to thank for financial support from Japan Society for the Promotion of Science and National Science Center of Poland, and to you for your attention.